Okay, hello everyone, and welcome. Thank you for coming to listening to me speaking about accelerating insights with real-time intelligence in Microsoft Fabric. So my name is William, and who am I? I'm a data platform engineer at Altro, an Oslo-based consultancy company. I have a master's degree in applied mathematics, specializing in statistics. And in my working life, I'm specializing in Microsoft Fabric and Azure, as well as Databricks and Spark. And on my free time, I'm also a very amateur runner here after my first half marathon with my friend who did it a little bit faster than me, so we won't dive more into that. So we'll go to the contents of this presentation instead. So I'm going to start with presenting some real-life business cases that we want to solve. And I'm going to talk about ingesting real-time data, first from something called MQTT, and then ingestion and transformation within Fabric, and also storage within Fabric. Then I'm going to split the business cases up a bit to some near real-time business cases and daily business cases. Before we'll wrap up by talking a little bit about acting in real time and finally connecting all the elements. So let's start with the presentation of the business cases from real life requirements. And these requirements comes from Tida, which is Norway's second largest mobility company. And they drive buses both on state and municipality contracts and also commercially in Norway and Denmark. They have over 5,600 employees and over 2,300 buses. And each day there are more than 20,000 bus and tram departures. So you can imagine there's quite a lot of data at Tida. So the business cases we are going to talk about is firstly data to the driver app. So the drivers have access to an app that gives them a lot of information, for example, of what bus they are going to drive that day when they come to work. So what we will focus on is the GPS position of the bus. So getting that into the app will make it a lot easier for the driver to find the bus that they are going to drive that day, because the buses are parked at very large parking lots, and if they don't have a sense of where to go, then it's going to take quite a long time to find your bus for the day. Also, we will talk about measuring the temperature inside a bus. Because of contracts, they require the temperature inside, so the passenger temperature, to be within a certain threshold. So not or falling outside of this would maybe lead to losing some money, or keeping inside of it would result in making bonuses. And lastly, the fuel use of a bus. So here we have three different fuel types of the buses. So electric, biogas, and diesel. So of course, when you drive a diesel bus, there is going to be CO2 emissions and climate gases. So if we can cut down the fuel use, it wouldn't only be a good cost-saving measure, which it is. It saves a lot of money. But it will also help the environment. And it's also hypothesized that driving that causes low fuel use is often better driving for the passengers, which is very important to make sure that they have a nice ride. So I want to do a split of the business needs. So one in near real time and the other daily. So in near real time, we put the data to the driver app. So that's because if we look at the GPS position, for example, you wouldn't get any useful information if this was updated 14 hours ago. Then the bus could be anywhere. but you need to have it pretty close up to real time, but it doesn't have to be this specific second. It's often enough, maybe in a 5-minute range or a 2-minute range. Whilst for the other two business cases, we report daily, so we don't have the need to report in near real time. So the temperature and the fuel use, measuring those, would go into to reports and aggregated up. And this separation is unique for our case. So many business cases across industries would, for example, require temperature in near real time. For example, if you have a hospital that has medicine in a freezer, if that temperature rises above a certain threshold, then you need to do something right away. But for us, it's more reporting needs. And even though two of them are classified with daily business needs here, real-time intelligence is still important because the data is inherently real-time. So that's the way we get the data in real time. So let's skip to the ingestion first from MQTT, which is the de facto exchange protocol for IoT messaging. And it's a scalable publish and subscribe protocol. So how does it work? Well, assume we have a lot of buses here to the left. They all contain IoT sensors, a lot of them, which we want to get the data from. So what do? Well, they connect to an MQTT broker and they publish some data. So that might be degrees in this case. So we can see that the first bus has 22 degrees and then 21, 15. All of these are plausible. Then you get one with 53 degrees. Might not be as plausible, but if the sun has been on the bus a long time with all its windows closed, it could be possible. But it's good to keep in mind that with IoT sensor data, there might be some spikes in the data sent, so this might not be a reasonable temperature. So the buses publishes the data from their IoT sensors into an MQTT broker, but we are here on the right side. So how do we extract the data? If we look at the first bus here, the one publishing 22 degrees, what we need to do is subscribe to the MQTT broker. So we subscribe to what's called topic inside the MQTT broker, which allows us to gain access to this topic and the data within it. And when we have done that, the MQTT broker again publishes the data to us. So we want to get this MQTT data into Fabric or into what's called an event stream, which we'll come back to. And there's recently a default support for MQTT directly in event stream, but it only supports version 5 and not version 3.1.1, which is needed for us. So we need to use a little workaround here, and we use a Spark job definition. You might be familiar with the Spark job definition. It's a part of the Fabric ecosystem as well, and you can create it as you can see in the red box here. So why do we choose Spark job definition? Well, you can run custom Python code continuously, and it's an asynchronous code that subscribes to the MQTT broker and formats the data in an event hub format. And finally, it pushes the data to an event stream. So I won't go further into this workaround. Just keep in mind that we had to do a workaround to get the data in to Fabric now. But in the future, I think that the version 3.1.1 would also be available for default connection in the event stream. But we're going to jump to ingestion and transformation with an event stream in Fabric. So let's take a step back to this one. This is now our focus, these two people, which represents now a Spark job definition which sends the data again to an event stream. But what is an event stream? Well, you can use it to ingest real-time data into Fabric. You can transform the data in real time and route it to various destinations. And you don't need to write any code to do this, so it's a no-code solution. Whether you like that or not is up to you, but at least it is. So Event Stream supports many default sources, as I said earlier, MQTT version 5, but you also have some other ones, so Azure Event Hubs, IoT Hubs, also Google Cloud PubSub, and Apache Kafka, and Amazon MSK Kafka as some examples of default sources. And you also have change data capture for certain databases. And you can also subscribe to events. And you have a lot more default sources, but it also supports what's called a custom endpoint. And that's what allows us to send the data via a Spark job definition. So if you were to connect to one of the default sources I showed you in the last slide, then you would press the use external source right here. But we can't do that, so we use the custom endpoint. And if we do this, we get this so-called edit view of an event stream. So we can see that the source is created here, which we've called MQTT. Together with that, a default stream is created, so a default stream of the data, and that gets the name from so MQTT ingest ES. And then the stream will get the name MQTT ingest ES - stream. But how do we connect to this? Well, we can press the publish button up top here, which gives us this view. So we were in the edit view, now we are in the live view. And we can see that pressing the source here, this MQTT, we get up a details page. And we can see 3 different protocols, so Event Hub, AMQP, and Kafka. So we chose Event Hub in our Spark job definition, so we transformed or formatted the data in an Event Hub format. So that's why we also choose Events Hub here. We can see some basics about it. We can see what its name is and its custom endpoint and whether or not it's active. And we can also press this SAS key authentication, which will give us a connection string, which we again can use in our Spark job definition to push the data to. So this is what you get when you create a new event stream, but now nothing else happens after the point of ingestion. It's not transformed, it's not stored anywhere. So what do? Well, we go back to the edit view and we can see that we can do different transformations. So there are some predefined operations. The first one is filter. So that's filtering out data, for example, null values or remove test data. You also have the manage fields transformation, which allows you to add, remove, change data types, or rename fields. Also, aggregate will allow you to do sums and maximum and minimums and averages over a period of time. Then we get into something familiar from SQL, which is join. So that's basically the same. You combine data from 2 streams based on a matching condition. We also have group by, and that might be a little bit weird because we have aggregate, but it's group by is like aggregate, but it has more complex options and more complex options for time windows. So in addition to the ones for aggregate, we can calculate the percentile, the standard deviation and variance, and count. And we also have more window functions available, like hopping window, sliding window, and tumbling window as examples. Going back to something more familiar is the union that's connecting 2 or more nodes, just like we're used to from SQL. And lastly, we can do the expand transform. And this will create a new row for each value within an array. So that's what you would call explode in SQL. So let's say we have done a lot of transformations and get the data into a format that we are satisfied with. What can we do then? Well, we need to store it somewhere or route it to a destination. So here we also have some different choices. The custom endpoint, for example, it lets you connect your own applications and consume data in real time from those applications. We can also route the data to a lakehouse, which will save it in a Delta Lake format, or to an event house, which I would prefer over a lakehouse. And this contains one or more KQL databases, and it's optimized for real-time data. And we'll come back again to the event house later. We can also create what's called a derived stream. So after the transformations, this could represent the transformed version of the default stream. And this can also be routed to different destinations and used across the organization. And lastly, we have the activator item, which is an intelligent agent connecting the data and monitoring and acting. So for example, you can alert users if something happens to your data. But that's a lot of theory, so let's go into a real-life example. So here we can see how an event stream can look, and it doesn't contain all the transformations, and it doesn't contain all the destinations, but there is some of them here. So let's start at the beginning. We've already seen this ingestion part, but we can also, by pressing on the default stream here, we get up a data preview tab. So here you can get a sense of what your data looks like directly from the source. So let's zoom in to this bit here. We can see that it has this form. I've shortened down the JSON a little bit so it fits. But we have some nested JSON structure. And we also have, for example, in metadata signals, we have an array. So we have some different data types and a nested format, which we might want to do some transformations on to make it a little bit prettier. We can also see a data insights tab and not just a data preview tab. So that gives you information about the messages and the count of them in this case. So we can see that there is some sort of variability throughout the day, which makes sense because around 3-4 o'clock in the morning, there's not as many buses out driving as there is in the middle of the working day. But now we have our untransformed data into our event stream. So what might we want to do first? Maybe we want to do a filtering, and pressing on this filter activity or transformation, we get up some details about it. So the name and the type and the configuration. So the configuration is what it does. So it says that the external ID does not contain test. So if we had this row or this row value, where we can see that vehicle external ID is 123 test bus, then this would be filtered out and we wouldn't keep it. Now we want to move on to using the manage fields. So again, pressing on it will help you see the name and the type and the configuration. So we see that the external ID that we saw earlier, we rename it to vehicle ID. And also vehicle timestamp becomes timestamp UTC, and we also change the type here. So it goes from being a string to being a timestamp type or a date time type. And we also do some more renaming down to make it consistent with what is already in the rest of the data platform. So this is how it looks untransformed. But what happens when we do the manage fields is that it turns into this. So it's actually one big long row, but I had to do it in 2 lines to make room. But we go from 1 column to 9 columns. So we unnest the JSON and pull out the information and give it the correct name in the columns here. And also, as I said, timestamp UTC has changed its data type to be a timestamp type. So you can still see that we have an array in the signals column, but that might be fine. So let's move on to the next one. We created a derived stream. So this contains cleaned data in an unpacked tabular format, and it can be routed to different destinations. And it also has a data preview and a data insight tab, just like the first stream that we looked at, the default stream had. So as you might see here, it is routed to 2 different destinations here. Let's go up first. Here we have some storage. So I think that the data we got from the transformation managed fields is in a good and clean data format, so it's ready to be stored. So we have this activity here. We can see the details pane again. Just one note here, for example, in name BAS KQL bronze konsat, BAS, it is bus as a service. We can also see the type and the status if it's active, or we can make it inactive. And we see some related items. So the custo item is where it's stored, and the custo table is in what table it is stored. So let's look again at the data insight tab. What we see here is that it has the same general form as the last one, and we can see the input events and the output events here. So the input events is in pink, but it's overlaid by the output events. So that's why it's a little bit difficult to see. But that's from the underlying engine, which ensures that if something comes in to be stored, then it will also be stored. You also have a data preview tab and a runtime logs tab for this. So the data preview tab is like we saw earlier, and the runtime log will help you to debug if there's anything wrong with the data. So now we have stored one table in an event house. If we go back to the derived stream and follow it the other way around, I thought it would be nice to also expand this column. So what happens when we do this expand? Well, 1 row becomes 6 rows in this case. So the first element of the array becomes the first row, and similarly for the other ones. So we have expanded or exploded the array in the signals column. But it still is in a JSON format in the rows, so maybe we could use manage fields again. So using that, again, we see that, for example, name becomes signal name. It's supposed to be there. So using the manage fields on this column, we can extract the values from the JSON structure again into 2 columns instead. And then we have done some extra transformations on this this table or this data stream. We can store it as well in another table. So it's the same as the last event house storage we saw, but we can see one different thing, and that's that the input events and the output events no longer are overlaying. So why? We see that the input events are much smaller than the output events. Well, we did an expand, right? So in our example, one array with 6 values became 6 rows. In real life, there's closer to maybe 20 array members, which then would be 20 rows. So maybe you can times it by 20, the input events to what will be the output events to be stored. So let's take one step back and look at the whole flow of data again. We start with our custom endpoint and our default stream, which is created when we create the event stream. We do some filtering to remove test vehicles, and then we unpack, rename, and change types of the columns before we create a derived stream, which can be used elsewhere as well. One path we follow is up and storing in an event house, this table, whilst the other one is going and expanding the array before we unpack it again, and we store in an event house again. So I've spoken a lot about event house now, and I want to speak even more about it. So let's go back one step to this. What are interesting now? These people have become one more. So we start with the Spark job definition, go through the event stream, and then push our data to the event house. So why the event house? Well, you can store and analyze large volumes of data, and it's like a workspace of KQL databases, so one or more, and you can compare it to what a Fabric workspace is for Fabric items. And it's automatically indexed and partitioned based on ingestion time, and you can ingest data from multiple sources. So we've seen event stream sources, but you can also, for example, push it from a data flow if you want. So when you have an event house and you open it, you will get an event house overview. So this gives you the situation of the event house. So on top here, we can see the storage in the event house. In this case, it has an original size of about 1 terabyte, but it's compressed down to approximately 174 gigabytes. We can also see what percentage, so 17% of the data is in premium cached storage. But the rest is in standard storage. So you can compare this to an Azure blob with hot and cold storage. We can also see here the storage resources again, one lake availability I'll come back to later. But down here we see the activity in minutes over the last 30 days in this view. So we can see that, well, we have about as many queries to the event house based on the day. So it's not a very much disturbance there. We can also see how many rows were ingested in the last 30 days again. So you can see here it's also a little bit of a variability. So it doesn't only have this variability in one specific day, but also in a month. So that might also make sense because buses don't drive as frequently on the weekends as they do on the weekdays. We also have some information about the top 10 queried databases, which is very simple for this example because there's only one. And we can see how many queries there were now it's in 1 day, so approximately 6,000. We can see how many errors there were, and luckily it was none. And the duration in minutes of those queries, so it's about 14%. We can also see that approximately 1.2% of the queries missed the cache. So that means that they had to go to the standard cold storage to retrieve the data. 1.2% I don't think is too bad, actually. We can also see the activity in minutes for the top 5 users there. So we can see that the number 1 user is an Azure Active Directory app which we have granted access to this event house. Lastly, on the right here, we can see the region it is in, when it was last ingested. Today, this minute, it's in Norwegian. We can also see some URIs for both querying and ingesting. So you can also ingest using this URI. You can also choose the minimum consumption if you know what that should be, or you can have it on demand. But let's go one step down in the event house to a KQL database. So pressing this, we get up the KQL database overview. So it's similar to the event house overview in some way. But we can see on top here the data activity tracker. So it shows us the ingestion and the queries in the last 3 days. We can also see the tables. I've filtered it out to contain the 2 that we have stored here in our event stream, and we can see some data about these tables. For example, how many rows were ingested in the last 24 hours and its size, and also how much data was ingested over the last 7 days. To the right here again, we have some more information. So firstly, the size, that will be the same as for the event house in our case. We have something about one lake, which I'll come back to later, but we also have the overview. And one thing to note here that's different from the event house is that we have a caching policy of 14 days. So after 14 days, it gets removed from cached storage and moved to standard storage instead. And we have an unlimited retention policy on the whole database, so data isn't deleted. It stays there forever, basically. And to the left, we can see the tables, and if you have shortcuts or materialized views or functions in your KQL database, you will find it there. We also have what's called the entity diagram. So for our 2 tables, we can see that, for example, this table has two materialized views that depend on it, whilst this one doesn't have anyone. So this is sort of a lineage graph within the KQL database. But I want to take a step back to our business needs. So what have we done up until now? We've done the same for both these cases, except for some different transformations. But I think it's time to split them up now because they are not similar from this point on. And I want to start with the near real-time business case, which is data to the driver app. So going back to the KQL database overview, this is the table we are interested in for this business case. So pressing into it, we get the driver app table overview. So we can again see a data activity tracker, but we also see a data preview here. And we can recognize some of the columns, for example, signal name and vehicle ID and timestamp UTC and signal value, and also the GPS position, which will be needed. So what we can note here as well is that for this table, we have set a retention policy of 14 days. That's because it's very, very rare that we want to access data that is more than 14 days old. That data would probably be outdated in this case. We can also see some details about the size of this specific table and also the count of rows and the rows ingested in the last 24 hours. But we want to make some aggregations on this table because we want to provide the last known GPS position to the driver app. So what we look at then is these related elements, which are materialized views created on top of the table. So that's what you saw in the entity diagram as well. So the materialized views we create in a KQL query set. And a KQL query set is a Fabric item which you can use to write KQL code and query tables. You can use it to create visuals, and you can also use it to create materialized views. So here, for example, we create the materialized view DWH consat fact last GPS position new, which implies that there is an old one as well, and I'm not very good at naming things, which is correct. And we create it on the table. So we do some stuff, some filtering and some changing of types and some substrings. It's not really important, but the important thing is that when you query this materialized view, you will get for each of the vehicles its last GPS position. So stepping one step back, we can, for example, give access to a service principal to this KQL database. So we can look at the top 100 queries in this query insight. So we can see that in many of the cases, it's an AAD app, but in some of the cases, it's me as well, querying or doing something from this KQL database. And we have given access then to this service principal and given them this query URI on the right side here. So when they have access and they have the query URI, they can ask the materialized view to provide them with the last GPS position in this case. So the complete flow for this business case is that we start with an MQTT broker, which we use a Spark job definition to ingest into an event stream, which we do transformations and then route the data into a KQL database within an event house. Then we can use a KQL query set on top of this KQL database and give access to a service principal to retrieve the data to the app, which can make it available for our everyday superheroes, the bus drivers, to make their day as easy as can be. So I also want to show you how this looks from the bus driver's perspective. We can see here, it's in Norwegian because it's a Norwegian app, so it makes sense. But you can see here you have different buses. So if we choose this one, 7523, we get up a screen about the bus, much information, for example, if there's any damages to it that needs to be fixed, and also its fuel use. But we can also press on top here, find in map. And if we do that, we get the map of its last known position. So in this case, it was updated 5 minutes ago, and it was on this E16, E39 road. So this allows the driver to find where the bus last was seen. So just mentioning that this app is not created by me, but by the capable developers at TIDA. But some of the data is supplied via Fabric. I want to move on to the daily business cases now. So the fuel and passenger temperature data. And moving back to the KQL database overview, the rightmost table is the one we are interested in now. And we can see that there is one difference between these two tables, namely that the one lake latency is available in the rightmost table. So let's press into it. Then we get up the overview of this specific table. Previously, I showed you the data preview, but we also have an option to see schema insights. So for example, here, the event type column sends most vehicle event type odometer. So this gives you also insights into the schema of your table. We can also see to the right, as we saw previously, the size. And skipping this a little bit down to the overview, we see that the retention policy here is unlimited because we want to use this for reporting needs. But back up to the big difference between the two tables is that one lake is available now. So the one lake availability is enabled. So we can see some information about that. We can see when it was enabled, and we can also see the latency. So that means that the data has become available within the event house, but it's not yet available within one lake. So that doesn't really matter for us, as we are aggregating up to maybe days, and reporting only daily. So 1 hour here and there, it doesn't matter, because it gets you get it with the next refresh. And so how can we then get access to this data? We have enabled one lake availability, but what now? Well, you could, for example, go to your lake house and create a shortcut. So many of you have probably seen this before. I'm in the lake house now, and we can press the get data and a new shortcut. So what happens then? You get some choices. You can choose your internal source, being Microsoft OneLake, and then you can find your KQL database, and then find your table within that KQL database. And it's as easy as that, and your data is available in your lakehouse, depending on the latency, of course. So what can you do after that step? Well, you can integrate it with batch data, for example, in a notebook. Then you can use Spark SQL as you're used to, or PySpark, SparkR, or Scala. And you can join it with batch data or other types of data to enrich it. And of course, it can also be used in other Fabric items, not just the notebook, as long as it has access to this lakehouse that you shortcutted it into. So what do we want from enriching it? Maybe we want the trip and route of the bus to compare across. Is it some buses that spend a lot more fuel on certain routes than other ones? It's also very important with the fuel and vehicle type of the bus, because comparing an electric bus to a diesel bus wouldn't make any sense, both in regards to the units, but also the numbers would be completely different. And similarly, a large bus, we would assume, uses way more fuel than a small one. Also, the contract the bus belongs to might be interesting. So what cost center is it? And many other things based on your business needs. So here you can build up a data model, maybe using a medallion architecture, if you like, and create dimensions and fact tables. So you get even more data and even more dimensions to your data, which will help you make more reliable insights. So what can you do next when you have created all of these dimensions and fact tables? Well, you can, for example, create a semantic model, and this contains then the relationships and business logic. And you can create one or more Power BI reports on top of it for visualizations and insights. And it can also be consumed via an XML endpoint. You can also use, for example, the API for GraphQL, which is available in Fabric. So it doesn't need to be a semantic model. This is just one example. So the complete flow for this, or these two business cases, is that we again start with the MQTT broker, go through the Spark job definition and the event stream, and save it again in a KQL database in an event house. But then we make it one lake available, and we can use it in a notebook to create our dimensions and facts, maybe using a medallion architecture. And we can present the data to the audience or to the users via a semantic model and or a Power BI report. We are nearing the end, but something I want to speak a little bit about first is acting in real time using Activator. So I'll briefly go through some of the advantages of Activator, but it's quite a large topic, so we don't have time to go into depth with it. But if you find it interesting, I would recommend you to try it out yourself. So what is the activator item? Well, you can use it to act based on patterns or conditions in your data. As we've seen, it can be used as a destination in an event stream, but it can also be used, for example, with KQL query sets. And you can use create your own custom rules and thresholds to alert via email or Teams, or kick off, for example, a Power Automate flow or a Fabric item. So I want to go through one example of this, and that's alerting with a KQL query set. So for example, we can check if the ingestion is still running. So here we have our table that we want to check if gets populated or not. And we filter it by saying that the ingestion time needs to be between 1 hour ago and now. And we do a count. And then we filter again where the count is less than 1, which means the count is 0. So no new rows. Only in that case will this query return something. So what do we want to do when it returns something? Well, we can set an alert on it. And we can see here that we can run the query every 5 minutes or an hour would be feasible in this case. And you can choose everything between, or not everything, but something in between 5 minutes and 1 day. We can also see, well, we check it on each event. So on each event that this doesn't happen, what do we do? Well, we have an action. We can send an email. Maybe we're saying, hey, come on, something's wrong here. Please fix the ingestion because we're not getting any more new data. Or similarly in Teams, but we can also run a Fabric item. So for example, a data pipeline or a notebook. So if we know that it is a volatile solution, so to speak, or you know what to do to fix it when there's no more data coming in, then you maybe could write a script to fix that automatically, and this could kick off that script. We also have the location where it is to be saved, again in BAS, Bus as a Service, and in our activator item called Alert RF. So in this, you have much more things you can do if you open up the UI of the activator item. But this is a simple way to create an alert on a specific situation. So other uses, as I said, destination and event stream. You can create it from something called the real-time hub, which we'll speak about soon. And you can create alerts from Power BI reports and dashboards. And you can create objects and rules also within the activator item UI, as I said a little bit about. So you can do much more when you open the item itself. But we don't have time to go through everything today, unfortunately. The real-time intelligence is quite a big topic. So I want to connect the elements at the end now using something called the real-time hub. So you might have seen this one before. This is the start page of Microsoft Fabric. And down here, we can see something called real-time, and this will open the real-time hub for you. So here we can see all the data streams that are available or that we have access to in our organizations. So we can, for example, see from the top here, the second one, if we remember back to our event stream, this is Kunsat ingest MQTT stream. So this is our default stream from earlier, right? And this one, again, is our derived stream. We can also see the tables that we created and push data to from the event stream into the event house bas KQL. And I've just whitened out some of the other ones that doesn't really matter to us right now. We can also connect to other data sources right here. So let's do that. So here we get up some recommended ones. You can also search or filter on the different, if you want Microsoft sources or if you want CDC, so change data capture for certain databases. Or you can play around a little bit and do some sample scenarios, for example, bicycle rentals or stock market. And you also have some recommendations. So for example, Azure IoT Hub and Azure Event Hubs. But in addition to connecting to new sources, you can also subscribe to, for example, Fabric events through the Real-Time Hub. So here we have three different options. So let's start at the top with job events. So these are events that are produced if a job is, for example, created, or if it succeeds, or if it fails. So you will listen to those events, you will subscribe to those events, and if, for example, a job fails, you want to do something. Maybe you want to start the job again or start another job, because if you want to start the job again, you could just use retries. But say you want to run a notebook or run a data pipeline or something like that when a job fails, then you can use this to subscribe to it. You also have OneLake and workspace item events, and these go on the creation and deletion and renaming of either OneLake files and folders or items in a workspace. So if you create a new item in a workspace, you can do some action based on that. What you want to do is up to you. We can also see the subscribe to some Azure events. So in this case, Azure Blob Storage events. So these are events that are produced when a blob is either created, deleted, or renamed again here. So this can be useful, for example, when you want to get data from an Azure Blob Storage account. A new file has just arrived, but you don't know it if you don't use this. So when do you pick up this file? Well, this can help you and tell you that, hello, a new file has arrived. Maybe we should start this ingestion, and it can start it for you as well. It doesn't just have to tell you. So that's the real-time hub. It sort of connects your real-time objects. And I want to finish everything up with a short summary of what we have learned and the different parts we have been through. We start with getting the data from an MQTT broker in which the buses sends IoT data to. A lot of data which we can subscribe to using a Spark job definition. This formats the data into a format that is compatible with an event stream, and then can push the data back into that event stream. In your event stream, you can transform the data and you can also route it to various destinations, and you can join data, you can union, you can manage fields and filter and all of the stuff that we have talked about. And again, you can push it to destinations, for example, a KQL database within an event house, where it is stored, and you get information about your tables down on their level, but also on a superior level of the event house and the KQL database. We can then use, for example, KQL query sets to create materialized views on top of that, so that we can grant access to other people or service principals to query from those materialized views and make that data available, for example, in the driver app. We can also enable one lake availability and use the data in a notebook or data flow or anywhere else through a shortcut in a lakehouse. We can here go through a medallion architecture, create our dimensions and facts, and maybe create a semantic model with all the relationships and also calculations within the semantic model. And on top of that, create a Power BI report for consumption by the end users. We also have the activator, which allows us to act in real time. So when something happens to your data, you want to do something. So for example, an alert if there is no new data, or to kick off an ingestion when a new file has arrived in an Azure Blob Storage account. And finally, we spoke about the real-time hub, which connected the different elements together in your real time. So that can be seen as a sort of a one lake for your real-time items. I hope you learned a lot today, and thank you all for coming. Thanks also to Ben and William for organizing, and Brian Bunk for helping me along the way. I would also recommend you to try this for yourself. Either use some sample data or use some other available data and just try it out and get a feel for it. And also for my fellow Norwegians here, a happy Constitution Day tomorrow. And I hope you enjoy that as well. So thank you all for coming and watching my presentation.